All right, so get out your notebooks. We are starting a new section today. This is not tethered to the book, so it's not section 2.1 or 3.7 or anything else. It's just entitled Stoichiometry. Yes, sir? I haven't graded any of them yet. Did you try and turn this in today? Yeah, I'll take it at the end of class. All right, so the section we're starting, so start on a brand new page in your notebooks. Update your table of contents. This section will be called Stoichiometry. And like I said, so this is not tied to a book section, but it will, I don't even know if we will end up in the book at all for this section, but your notes need to be in here for this. So what we're going to start with is an equation. So nitrogen plus hydrogen yields ammonia. And I'm going to represent this symbolically. Like this. Triangles and circles. You're writing this in your books, drawing this, whatever. Again, we're just, this might even be similar to that equation we've used over and over where hydrogen and oxygen yields water. This is a similar one, but this is going to help us visualize this equation. So what do you notice right away that should be hopefully making you guys kind of itch? Not balanced, uneven. How can we fix this? Add some more hydrogen? Let's add another hydrogen in here. Does that fix it? No. What do we got to do? One more? And then another one of these, right? How's that look now? Good. I agree with you. Now, here is the trick. For us to run this equation, this reaction, for us to do this one time, how many molecules of nitrogen do I need? I use that word carefully. How many molecules of nitrogen do I need to run this once?
2.
Okay, I heard a 2 and a 1. Some of you are right and some of you aren't. A molecule of nitrogen. What is a molecule of nitrogen? Nitrogen is diatomic. So when I'm referring to a molecule of nitrogen, I'm talking about N2. If I said how many atoms of nitrogen, that would be a different number. That would be the 2 that you're talking about. So let's see if I can do this. So to run this one time, how many nitrogen molecules do I need? How many hydrogen molecules do I need?
3.
And how many products, how many ammonia molecules do I create?
1. 2.
You sure?
Nope. Yeah.
How many nitrogen molecules did we create? 2. Good. Now the trick is we have to do it in this format. If we only have 2 hydrogen molecules, can we make this reaction happen? No, why not? What's that? Not even. We don't have enough. right? If we only had 2 hydrogen molecules, we could make one of these, but then this one would be incomplete, right? And the way reactions work, they have to be completed. You can't have kind of part of a reaction happen. You can't have a nitrogen floating around here with just 1 hydrogen attached to it. It has to have another for this reaction to progress. That's how these chemical reactions work. You have to have these completely react. So let's run this twice. If we run this reaction twice, we want to do a whole reaction twice, how many nitrogen molecules would I need to run this equation twice? 2. How many hydrogens would I need? And how many products would we form?
4.
Let's keep going. What if I did this 100 times? How many nitrogens would I need, nitrogen molecules? 100, right? Look at your notes. You can't see it on my board because I've scrolled up. How many hydrogens would I need? And then finally, how many products would I form? So now let's get really crazy here. You can see a pattern forming, I would hope. Let's run this reaction many more times. Let's in fact run it 6.02 times 10 to the 23rd times. How many nitrogen molecules would I need to run this that many times? 6.02. Now, I don't want to write that over and over and over because awful. What way could I shorten that number? Just like if I said, hey, I want to run this a dozen times, we could say, well, you would need a dozen nitrogen molecules, right? How many hydrogen molecules would I need here? 3 moles. And then how many products would I form? Do you understand now why I'm doing this?
Yeah.
What has been consistent through all of these examples? Ratio. What is that ratio?
1:3:2.
So now let's come full circle. Let's snag this. Let's copy it. Let's go all the way back up here. I'm going to paste in that ratio that we just had. Where do you also notice these same 3 numbers? What do you mean in the equation? They have a number. They have a name. Come on. What's the name for those numbers in the chemical equation? Nope. I think maybe BK, did you say it? The coefficients in the balanced chemical equation. Now, we're not going to write a 1 here, but this was a 3 and this was a 2, was it not?
It was.
This is what we call the mole ratio. In a chemical equation, in a reaction, the reactants and the products combine and form in a way that matches the mole ratio, which is simply the coefficients of the balanced equation. So let's do a thing. You'll notice the reaction here listed is somewhat familiar. because we've been talking about it for the last 7 or 8 minutes. Helgeson can tell us exactly how many minutes. 10 minutes and 13 seconds. And counting. And counting. Okay, so looking at this sheet, consider Model 1. What are the coefficients for each of the following substances in the reaction? What are the coefficients? 1A. We literally just did this. 1 for nitrogen, 3 for hydrogen, 2 for ammonia. Draw particle models below to illustrate the reaction. You just did that as well. Boy, chemistry is so easy, right? Right? Right. And now on the bottom here, you've got a grid. Now it doesn't ask you the same thing I did, but it's got similar numbers, and you guys can figure that out. Turn to page 3 of this worksheet real quick. See where it says stop? Okay, so by yourself or in small groups, I want you to work through this worksheet packet, reading the questions, thinking about what we just did on the board, and discussing it with your, whether it's lab partners or a friend or whatever. See if you can get to the end of this where it says stop. At about 11:03 or 4, we will come back to our seats and we will talk about something a little different. That will be the worksheet for tonight's homework. So you can do that now. You guys can kill the thing. All right, so in this worksheet I just handed out, it starts with this equation. What do you notice is wrong with this equation right off the bat? It is not balanced. Okay, how would we balance this?
Put a 2 in front of the NO, and then a 2 in front of NO2. Wait, no, that wouldn't work.
Oh.
Yeah, it would. No, yeah, it would.
Take your time.
I just said
Mr.
that.
Clever.
Is it right?
This is right, 2, 1, and 2. So, what is our mole ratio here?
2, 1, 2.
As written, this is 2 to 1 to 2, is it not?
Yeah.
Now again, these are different numbers than we had in the last worksheet, but this is also a different chemical equation. Every chemical equation is going to be different for that matter. So now let's look at number 1A. 2 moles of NO will react with how many moles of O2? 1. To produce how many moles of NO2? 2. How did you know that so quickly?
Because it says up front.
Yeah, that's just the ratio. That's the mole ratio. But now let's look at part B. Now this is asking us to find some kind of equality, which to me smells like a conversion, which to me sounds like a good use for a T-chart. Yeah, I know. Now I don't like how this problem is necessarily set up in B, so I'm going to write my own T-chart because reasons. But in this case, we're going to start with 3.6 moles of O2. I'm going to just slap this thing into a T-chart. Now again, without thinking about it, what can I immediately write down? Moles of O2. And now let's think about this, looking at our question in part B. What are we trying to get to?
How many moles of NO2?
Moles of NO2. Do I have a conversion, some kind of relationship between moles of O2 and moles of NO2?
2-to-1 ratio.
2 to 1, or probably best put as 1 to 2. Now you'll note I purposefully wrote down the units first and then filled in the numbers. And now how would I solve this? I can do this math in my head, I think.
Back cross, divided at the bottom.
7.
Now some things about T-charts when we're doing mole ratios. Putting the entire unit in here is critical. If you were being lazy before and just writing mole here and not what it is, you're going to have a bad time when you run into a conversion between moles of different things. You need to be precise and you need to be descriptive in your boxes on your T-charts, or you will quickly get lost. Further, in almost every T-chart that we've been doing before, what was always the number in front of moles of something? 1. Will it be now? No, it will be based on the mole ratio in the problem. So it's entirely possible that you will not have a 1 in either of these boxes. So let's do let's do letter C. Should I erase this or? Let's do letter C. You guys all had time to copy this? Hold on. So letter C, how many moles of NO must react to form 4.67 moles of NO2? 67 mole NO2. What can I copy without even thinking about it? And where are we trying to get to here? What is our relationship, our mole relationship between these? Hold on. I know what you're saying, and you're shortcutting this for the people that might not immediately jump to that conclusion. What number should I put in here? 2 to 2. Now, yes, it is just 1, and yes, it is the same thing. For those of you that are more solid in the math on this, you're absolutely right. Without thinking about it, can I get this answer? Yes. My advice when you are doing these is to just copy the mole ratio right from the coefficients, even if they're the same. Maybe in some case it might be a 2 and a 4. Yes, that ratio is technically 1 to 2. You can reduce that, but for the sake of filling these in, just copy the coefficients from the balanced chemical equation. And again, that is also the key part of this is none of this works if you do not start with a properly balanced chemical equation. You have to start there. None of this does any good if you've got a 6 here and a 7 here and a 3 there. You're going to have a bad time. So this is where balancing, that I know we haven't talked about in probably a month, now all of a sudden is critically important once again. And depending on what I give you in a problem, sometimes I might give you a balanced equation. Sometimes I will give you a blank one like this that you have to fill in. But ultimately, having it properly balanced and checking it is critical to being able to get this done. The homework tonight, you have plenty of time to get this done, is just the front and back of the first page in this packet. So it's, I think, 1, 2, it's 5 problems. But again, balancing those equations is going to be critical first.